analytical solution for Cooper pair box. Let's review what is a Cooper pair box, right? Again, it is just like a LC tank. But instead of having an inductor, we replace it by a Josephson junction. The reason is for anharmonicity, which we have not proved it. We will look into the details later. Understand more about anharmonicity later in this class. But anyway, replacing the inductor, linear inductor, but by this non-linear inductor, Josephson junction, we will be able to form two level, not this two level, however, it depends on actually, sorry. Anyway, we can form two level easily because it has anharmonicity, which I will discuss more later today, right? But let's take it for granted. We gone through the math to come up with the Hamiltonians, and then we promote the operator, right? And do you remember what are the conjugate variables? Sometimes I call it generalized momentum and coordinate for this system or for electrical circuit. What are they that we used earlier? Do you remember? Charge, yes, charge is the generalized momentum. And how about the coordinate? Remember? Flux. Yeah, flux, yeah. However, we don't want to work in that space. We then try to convert it into the lumber and also the phase. And the lumber, if you remember, the lumber is just the number of Cooper pairs, right? So it is just the charge divided by 2e. And negative, right? And the phase is nothing but just the flux divided by the reduced flux quantum, right? Let's just treat this as a review, right? We might not review this again in the future, but hope that you are familiar with this. N is just equal to the Q, negative Q divided by 2E, right? And then the phase is just equal to the flux. And this flux is just might not be the real magnetic flux, right? Because we associated, for example, the flux, we define flux as what? Anyone can remind me? How do we define the flux? In a circuit, we definitely have voltage. How was the relationship between voltage and flux? D flux, yeah. First stop, yes. D flux dt equal to voltage, right? So yeah, so we try to link this, right? Of course, the background is very profound. Probably you'll also not understand, but doesn't matter, right? We just take this for granted when we quantize the circuit. Okay, so with that, we came up with this Hamiltonian, and this is in the operator form. If we can solve this, we can solve the behavior of this circuit, the equation of motion of this circuit, right? And we have n hat minus ng, where ng is just a number, the offset charge, minus ej cosine phi naught. And then we just use the equation of cosine phi becomes half ei phi minus e negative I phi. And these are what we learned earlier when we quantized the Cooper pair without the coupling capacitor. But anyway, do you remember this, right? This one need to have m equal to n, this one need to have m equal to n plus 1, this one need to have m equal to n minus 1 in order to be non-zero. We limit into two levels, so this matrix become a 2 by 2 matrix. Eventually we get this. So of course we cannot review the math now because it's too long. But the most important thing is that after when we approximate it into two level, then we have this matrix. And we need to be very careful, right? This one I confused you one time, actually not a few times, one time. EC is the charging energy of one electron. The energy you will gain or you need when you put one electron charge across the capacitor, negative Q and plus Q. That is the energy, which is equal to half E squared over C. So in the literature, sometimes the EC is actually the charging energy of one Cooper pair. It means you put 2 electrons there. So it's going to 4 times larger than the charging energy of 1 electron, right? Because it's Q squared. So I put 1 electron, I have certain energy. 2 electrons, I have 4x more energy. So if you forgot, no problem. But you need to be very careful when we read papers, right? That is something you need to be careful about. Now, when I represent this in the matrix form, as we said before, whenever we represent an operator in a matrix form, it means you have chosen a basis. Make sense? So what is the basis here? What is the first column correspond to? Huh? Say again, someone say it. 0. How about the second column? 1. But what is 0 here? Of course, we can say it's the ground state, second column is the excited state. But what is the physical meaning here? For example, in spin Qubit, when we say 0, maybe we mean spin up, right? When, for electron, when the magnetic field points down. And 1 is spin down. So here, what is the meaning of 0 and 1? Say again? Huh? Number, of course. It means n, right? N equal to 1. Very good. The number of excess Cooper pair. Right? That is the meaning of 0 and 1. That's the basis state. And again, of course, their superposition will be the linear superposition of 0 and 1 Cooper pair. And that is the beauty of quantum mechanics, right? Like we have 1 extra or 0 extra people in this classroom, right? Okay, so we have this Hamiltonian. You don't need to memorize it, but you need to appreciate it. And what we did, the next step is we try to shift the energy, because you look at this, for 0, 0 ground state, you have ECC NG squared. This is ECC 1 minus NG squared. Just for convenience, we want to shift it, because shifting the energy level is not going to affect the behavior of the system. It only changes the global phase. So we minus this by the FH of these two energy. Again, last time we gave you an example. Energy is at -3, one is at -1. So I shift the reference to -2. Then it becomes 1 and -1. Make sense? You're on the third floor, another guy is at the fourth floor. Now I put the reference at the middle of third and fourth floor. Then one become -1 4, another become +1 4. Right? So I just shift it. Everything is just math, right? It would be good if you can go through it. If not, you see that after shifting, this is negative of something and plus of something. And then we further define an energy called E, equal to ECC times 1 minus NG. So there is something we can appreciate in this matrix. We have EJ. What is EJ? What is J? Josephson junction. So EJ means what? Thank you. That Josephson junction energy, right? That is a constant we learned earlier, okay? Which is related to IC, the critical current, and also the reduced quantum flux, right? Reduced magnetic flux quantum. I believe it's IC50. I might be wrong. I forgot the equation. I think this is this one, right? Probably EJ equals to IC. I believe so, right? Please check. I can be wrong, right? The important thing is that the behavior of these circuits depends on Josephson energy. So you can control it by changing the critical current of your Josephson junction, right? The critical current can be changed by changing the area of the interface, of the cross section. And how about E? E looks like nothing, but remember it is ECC times 1 minus 2 NG. So what is ECC again? The charging energy. Well, the charge of electron or Cooper pairs is constant, universal. So you can control it by changing the capacitance. So now the whole thing is that you can change the Hamiltonian as to anything you want by manipulating the capacitance and the inductance, or the Josephson junction area, right? And I told you earlier, this is just an artificial atom. And we cannot engineer the natural atom easily, or almost impossible, right? But just as an electrical engineer, as how you design a transistor in inverter, how you size the NMOS and PMOS, I can size the capacitor and the Josephson junction to achieve a certain behavior of this artificial atom. Right? That is the beauty of this. So at this point, this is just math. Hopefully you can go through. I probably won't ask you to derive, but I hope that you can understand the derivation. But after all, you say that the Hamiltonian is half of, it's easy to memorize, negative E and E, and then the rest negative EJ, negative EJ. And then we will look at this, right? So the first thing we saw is that I can decompose this this Hamiltonian into a vector product of this polyvector. Remember what is polyvector? It has three components, right? So if I can remind you, polyvector, of course, equal to X, sigma X, sigma Y, sigma Z. Whenever I write it in a matrix form, it means I also have chosen a basis. What is the basis for this one? Or in other words, I'm going to write here sigma X plus a basis plus sigma Y, a basis state plus sigma Z. What are these basis states? For a polyvector, do you remember? I say again? This is another vector. What I'm referring is to this. X hat, Y hat, and Z hat. Right? You should know that, but probably you forgot. Do you remember this? So you still use the three-dimensional basis, right? But however, the coefficient is the matrix, which is legitimate because we already learned what is a linear space, right? As long as you fulfill those criteria, it is a linear space. We don't live in this space, although it shares the same basis vector with us, with this where we live, right? And if I write this as this one, it also means this one is, I kind of have written BE equals to EJ X hat plus 0Y hat plus EC hat. Of course, this is, again, not a real vector in our space, but I try to map it in this way. This is in energy. It's not really magnetic field. And the reason I write it in this way is just that we see that this is similar to a spin under an external magnetic field. We have quantized, we have studied how to solve the Schrödinger equation of a spin under magnetic field, which has a similar Hamiltonian. So if we repeat the process, we will get the same result after proper substitution. That's what I want to say, right? So first of all, again, we have this Hamiltonian. We derive it, no problem. Then we try to decompose into this matrix. This is just a trick, purely a trick, a mathematical trick, right? It really doesn't mean that we have a vector in the real space like this, okay? Is that okay up to here? Then I can compare this to the spin qubit that we learned earlier. The only difference between these two is that the spin qubit, of course, is real physics, has gamma h bar divided by 2. Here I have 1/2. If I try to replace the B by EB divided by gamma h bar, then I can reuse all the equation I have derived in spin qubit. Right? Because if you just go through the same math, right? I forgot which chapter, go through all the math. You can get Lamarck precession, can get rapid oscillation or whatever. You will get the same thing, right? So for example, I showed that in spin qubit, the Lamarck precession, we have learned it is just gamma times the magnitude of the magnetic field. So for this one, we also have Lamarck precession. I just need to substitute B by gamma divided by h bar BE here, right? BE divided by gamma h bar. which gives me BE divided by H bar. And basically, it's just saying that I can really treat this like a spin qubit, right? And in spin qubit, we map it to the Bloch sphere. So now we can also map the same thing to the Bloch sphere. And that brings us to this page. If I just like what we did for the magnetic field, the magnetic field is real. It's in our real 3D space. We do have a direction of magnetic field. But now I replace this B by this BE. I still have EJX hat plus EC hat, right? And since it doesn't have Y component, so this fake magnetic field is always on the XZ plane. Again, this is not a real magnetic field, right? Let me remind you. This is fictitious magnetic field, right? It's not real. And also, it has unit is energy, right? It is not magnetic field, right? Because we, as I said earlier, what is E? E is J and E, right? Right? So basically, we have this one. Is this okay? So with this, we can, if you just map through this, then this state is n equal to 0, 0 extra Cooper pair. This state is n equal to 1, 1 extra Cooper pairs. So you basically can treat, or instead of treat, I would say, Cooper pair box qubit behaves like a positive charge spin qubit. Okay, so if you go through the map, it's just like we are doing with a spin qubit, but with positive charge instead of the negative charge. Okay? Is this clear so far? Yeah.
So that circuit is existing of
Say again, I'm sorry. Yeah. This is the precession. It precesses about the magnetic field, right? So this is the magnetic field direction. So it will precess about the magnetic field. And you will see that the direction is opposite to an electron because it's positive charge. It behaves like positive charge. So very clear, right? There's no charge here. We are not talking about spin. This is only 1 or 0 extra Cooper pair. That is the state. But the way it behaves on a Bloch sphere is just like a positive charge with spin, a spin qubit with positive charge. So we don't need to go through all the derivation, right? In principle, you can take this equation and then repeat what you have derived in the spin qubit chapter. You will get something similar, right? But now because I just do substitution, I know that I will get something like this. So this is the generalized Cooper pair, but as I said, this is approximation. Now we will look at a few important cases and to understand what they are. The first is that I have been talking about Cooper pairs, but now I introduce something called charge qubit. What is the meaning of charge qubit? A charge qubit, the definition of a charge qubit is that the charging energy is much larger than the Josephson energy. That is the definition of charge qubit. Okay, now we consider the first case, case 1, which make this not very important. We call something called sweet spot. Sweet spot means that Ng equal to half. What's the meaning of Ng again? You probably forgot, right? Ng is the Ng here. This is Ng, where we define E equal to ECT times 1 minus 2Ng. And Ng is the charge induced by this gate, the extra Cooper pair induced by this gate. So if you remember, I hope that I have the right equation. Ng is the offset charge. No. Right? It should be Ng should be equal to Cg times Vg divided by 2E. Okay, please check. I don't have this with me. Check, right, to make sure this is correct. But based on this equation, you understand what it means, right? It's just the gate and this capacitor induce a certain amount of Cooper pair. That is the sweet spot. So how do we control Ng? We control it by adjusting Vg, right? 0.1 volt, 15 millivolt or whatever, 1 volt, so that you have the right Ng. When you have Ng equal to 0.1 E, which is ECC times 1 minus 2 Ng, is going to be E0. Right? Because Ng is equal to 1/2, right? So 1 minus 2 times 1/2 is 0. So no matter what's your charging energy, E is going to be 0. So this is true, even ECC is not larger than EJ. But that is okay. We not only because I want to introduce the concept of charge qubit. Right. Is this okay? And what will happen to the Hamiltonian? Then it means H, which is equal to half, as I told you, right? E, negative EJ, negative EJ, E, right? I also remember the equation. Equals to half, 0, 0, negative EJ. The writing is so bad today. EJ, negative EJ. Because the diagonal terms are E, right? And they are 0. And this, if you try to write it down, is just equal to negative half sigma x, sigma y, sigma z times 0, 0, E, which you already know that because you already know the expression is there, except EJ now becomes 0, right? We already learned this. This is equals to this times this, and now E. Did I write something wrong here again? I think I wrote this wrong. I'm sorry, my cheat sheet is wrong. What is wrong here? Can you figure out? Thank you. E should be on the top. Very good. Right? Because, EJ, not E. Should be EJ, not using E, right? Where E is 0. Right? So this is E equal to 0 here, right? Now then what does it mean if I try to plot it on the broad sphere? Now if you look at this, what is the direction of E now? Because the direction of this BE now, E is equal to 0, right? So it's just pointing at the X direction. This is BE equal to EJ. X hat. Okay, that is the magnetic field in that direction. Based on this, just based on this, magnetic field is pointing in this direction. What will be the eigenstate? Just think about the spin. What will be the eigenstate of this system if the magnetic field is pointing in this direction? Remember when magnetic field in the spin qubit is pointing vertically, the eigenstate at 0 and 1, right? Now when it's pointing in the x direction, what are the eigenstates? Just look at the broad sphere. Positive and negative, plus and minus, right? Just look at the broad sphere. And that's why it's very useful if you can have this intuition, right? The broad sphere show me the eigenstates must be plus and negative. Okay? What is plus and negative, by the way, here? Plus 0 to 0 plus 1. And let me just spell it out. What is the meaning of 0 here again? Is n equal to 0 plus n equal to 1 divided by square root 2, and minus equal to n equal to 1 minus n equal to 0 divided by square root 2. Is this okay? And you're just telling me that if it's operates as sweet spot, the eigenstates of this system is the superposition of 0 and 1 Cooper pair, but with different phases. One is plus, one is minus. Do I do this wrong? Is it 1 minus 1, 1 minus 0, 0 minus 1? Huh? Anyway, I forgot. My brain is not working. But anyway, here shows the diagram. You see that here we have what? ECC much larger than EJ. And we have different value of NG. When NG is half, this is the state, right? This is the ground state. Maybe I call it minus, and this is plus, for example. Which one has a lower energy? You need to solve it, and I forgot which one has a lower energy, but anyway, so this, let me just call this ground, this is exciter, so I can save myself from that, but you can refer to the book, right? Because to know whether it's higher or lower, this is higher. So yeah, so plus should be, I think plus should be lower energy, yeah. Okay, plus should be lower energy, minus is higher energy. But this is the energy of the state. Can you see what happened if the offset charge go to left or right? Instead of 0.5, I get 0.6, 0.7. Do you see that the energy change a lot? And what is this offset charge? It is a charge that controlled by my inputs through the capacitor. Well, that is okay if I can have precise control. But if I don't have precise control, a little bit change in Vg is going to change Ng. But the Ng, when Ng change, then the energy separation, the qubit energy will change a lot. So it is very sensitive to charge noise because this is intended capacitor. But your system is coupled to the environment through other capacitor. You cannot ignore that, avoid that, right? There's always capacitance coupling everything to outside world on a chip, right? So then you will, if you have different charge, right? Then this is called charge noise. Then it means you are very sensitive. You're very sensitive to charge noise. your qubit frequency will change because originally this is your E01, this is your qubit frequency, but with a charge noise, your E01 dash will be very large. Right, from here to here. Let me just maybe remove this and just say that, right, like this one, the change is the charge noise. This is a very important concept. Do you understand what I'm talking about for charge noise? What is the meaning of charge noise? No? So, look at this figure. The ground state energy changes as a function of Ng. Is this okay? This is the ground state. This is the excited state. If I have 0.5, the energy difference between the excited state and ground state E01 is this much. If it is not 0.5, let's say it shifts to here, then this is the energy difference between these two states. Right? The energy changes a lot. So if I am not able to control Ng equal to 0.5, let's say it's 0.05, 0.49, then the qubit frequency is going to be on the side, right, instead of this middle one. So if I have some noise due to charge, and we always have noise due to charge because this guy can be coupled to another capacitor. For example, here is a node, and then I have an unintentional capacitor, and then it coupled to charge noise. I have a voltage here. I always have a capacitor, right? Capacitor you cannot eliminate. And I have some noise on the environment. It's going to couple to here, and then you're going to change the Ng. Then as a result, your qubit frequency will fluctuate, and that will reduce the coherence time. Okay, please ask if you have a question. I think I might not explain it well. Now then why this is called sweet spot when Ng equal to half? Because at this point, do you see that it has a zero derivative? So it means you change the charge, change the charge a little bit, the change in the value probably to the first order is zero. But of course, you still have a second order. Right? Because when this is flat, it means that even you change Ng, you won't change a lot, right? So you don't want to bias at this point, because at this point you change Ng, you will just change the energy a lot. And that is called sweet spot when Ng equal to half. Make sense? Okay. Let's continue to, which slide is this? Oh. Yeah, so here I actually make a mistake. I actually have something here. This should be 0 minus 1. I'm sorry. Okay, 0 minus 1. Because 0 is the ground state. Okay. So actually I've almost said everything I want to say from the previous slide. I also need to emphasize one more thing before I move to the next topic. So let's recall this again. H equals to half 0 negative EJ, negative EJ, 0, right? Of course, equal to negative EJ divided by 2 sigma x. This one we already know. I also can write it as negative h bar omega L divided by 2, 0, 1, 1, 0. Right? Where with H bar omega L equal to EJ. Okay, so basically for a charge qubit at the sweet spot, this is EJ. So you change the Josephson junction energy, Josephson energy, you will be able to change the qubit frequency, H bar omega L. H bar omega is the normal frequency, right? Right. So again, we already talked about the eigenvector. So yeah, I think I don't want to. Maybe I just write, okay. Yeah, I will just stop it here. Is that okay now with the charge qubit at sweet spot? And this is a qubit that has been used maybe 20 years ago. People start with this charge qubit. They want to operate in this sweet spot to why again? Why they don't operate in ng not equal to 1/2? Say again? What did we just say? When you operate in sweet spots, you are insensitive to charge loss. Yes. Yeah. So, right. So we try to operate at ng equal to 1/2 to be insensitive to charge noise, right? Basically, charge noise means delta ng, right? You might have delta ng. So this is not good. And it turned out this is really not good, okay? We will look at transmon later, okay? So now, a charge qubit, right, at sweet spot, we have two states. These are the eigenstates. And the eigenenergy will be plus minus h bar omega L divided by 2, or plus minus EJ. You can even say here is plus EJ divided by 2. Here is negative EJ divided by 2, right? And this is for the minus state. This is for the plus state. Okay, so done.